What we're going to do today is build a motor. Your homework assignment will be to answer some questions on this worksheet titled Exploring Motors. I'm going to go over all of that information here, but because this requires you getting a lot of supplies and I have to pass this out and you're going to be doing this at your seat, I'm going to give you some of the supplies now. We're going to talk about the theory, about how the motor works, and then we're going to build it, okay? The first thing I'm going to give you is the magnet wires. The list of supplies that you'll need are right up here. That's this red wire, okay? When you get it, you can tear off the tape with your fingernails and straighten that wire out so it's nice, smooth, and a straight piece. I love this lab because it's a good lead up to the one we're going to be doing, building our circuits, our metal detectors. And if you follow directions, if you pay attention to detail, you should be successful. If you're one of those people that just kind of rushes through everything and you don't think the details matter, you won't be successful. My personal goal on this project is that everyone have a working motor by the end of the period. I have yet to accomplish that. I've tried to improve and change the lab along the way, but there's just so many little things that can make it go wrong if you're not careful with how you follow the directions. I'm going to give you a handout here titled World's Simplest Motor. Okay? What I'd like you to do is, when you get this, look at the picture of the finished motor on the back. Let me focus this for you. This picture here, the finished motor on the back. Notice all the parts that go into that finished motor. We've got a magnet, a permanent magnet. We've got a coil of wire. And of course we've got a battery that hooks up to that coil of wire. And our paper clips here serve a very important function. But look at that and try to imagine what this is going to do. When you wind that wire into this coil, that coil will then spin. It's going to be flipping around, spinning, like so, okay? And that's going to be your motor. I want you to, on your own, read the theory of operation here on the front, okay? And as you're reading that, I'm going to give you the other materials that you can pass back. I showed you two different motors yesterday. I showed you my swing motor, and I showed you a more traditional motor, okay? In the swing motor, what we had going on is a permanent magnet and a coil of wire, and when I ran electricity to that coil of wire, it would swing towards the permanent magnet. It would be attracted. What kept that motion going? What kept that swing going back and forth with this one? Why didn't it just go here and stop? What was the secret to this one? Well, gravity carried it back, but normally I could just have it stick there. If this magnet is turned on, the electromagnet is turned on, these two would stick. What allowed this one to go back this way? Hint, hint, guys. I turned it off, exactly. I used this push button switch. And whenever the switch was engaged, was on, it would be attracted to it. Whenever I released it, gravity pulled it away. Get that? Attract, release. Attract, release. So it was gravity that was making it go the other way. That motor works on a different principle than the second one I showed you, which is more like a real motor, one that you might actually do some work. That was this one here. In the case of this one, we had our coil of wire and we had two permanent magnets here. And instead of turning it on and off, what did we do with this one to keep the motion going? It wasn't turning it on and off, it was what? How did we reverse the poles on this one? How do we change the north and south poles on the magnet? How do we switch them?
Brushes?
Correct. We use those little connections there, the brushes. So that leads us to our first question. Whenever you're looking at a DC motor, like the kind we made, it runs off of a battery. What three parts must the motor have? What did those have? Come on, guys. What three parts? A magnet, a permanent magnet, right? Got it here. Got it on these on the outside, the red and the blue, and a coil of wire, like the one on the cork there, like the one here in the middle that spins around in a circle, like the one you're going to make out of the red magnet wire. And the third thing you need is some way to do some sort of switching, okay? You need something to do the switching. In the case of our swing motor, that was my little push button switch. In the case of a real motor, it was this part right here referred to as the brushes. Remember, a generator has it, a motor has it, to allow you to change the connections. So you need something to do the switching. Now, your motor that you're going to make today and answer questions about, it also has a switch of sorts, but it's not a push button that someone has to do this with. It's one that will activate automatically, and it will turn your motor on and off at the right time. There's a question about that. It's the only thing I'm not going to spell out for you in the homework. You need to look for that in the design, in the construction. As we go through this paper, in this section right here, I give you a good hint about that. How we're able to turn this on and off. Okay? Now, this is an illustration diagram that explains how your motor works. And I ask a question on the homework. It says, explain the theory of operation. How does it actually function? That's what I'm going to explain right now. In order to get movement out of a motor, what do we need to create using electricity? Magnetism. That's the whole point of this. Electricity can create, and magnetism can create electricity. That's how a motor works. That's how a generator works. It's the theory behind a transformer. So many of these things. So what we're looking at here, this circle represents the loop part of your coil, okay? So we got that loop. And then there's a wire coming out of both ends. So we take the wire and we wrap it in a circle, and then this is the end of it. This is the beginning of the wire. And that loop is going to then sit in two paper clips, and as you can see in that picture on the back, it's going to be spinning like so, okay? This represents the, what do we call it when it's one that's always magnetic? Permanent magnet. So we have a permanent magnet. You actually have two. This is just showing one with a north and a south pole, but you have two stacked there, okay? So you put your permanent magnet underneath. You need something to be attracted to, like I had in this design. You need something to be repelled by. The permanent magnet provides that. When you hook this up to electricity, when you attach the little clips to your paper clips, electricity can then flow through your coil. Because it's direct current, it flows in only one direction. When we have direct current, we're going to get a north and a south pole, and they won't change. There is a way we could change which one is north and south. How could we do that?
Change the connection?
Yeah, if I change the wires, the connection, I can change which one is north and which one's south. But right now, this is what I get. And you can see the red and the blue. Opposites will attract. And this coil will want to do this. Boom. Okay? It'll want to turn down, like so. The red will be attracted to the blue, and the blue will repel the blue. So it'll forcibly turn it this far. Now, just like my swing motor we saw, if it weren't for the ability to switch it off, this would just go, touch that magnet, and stop. And that would be the end of our motion. Wouldn't be very useful. But because we have the ability to switch this thing off, like you see here, what happens is the coil now spins around, and when it reaches the bottom, just when it would get stuck, we turn off the electricity. If we turn off the electricity, it's no longer a magnet. And since it's no longer a magnet, then it can finish its turn and go up. Its momentum that allows it to spin the other half. So the first half down to here is with magnetism. Boom. The second half back to where it started is just momentum. That's why it's not a very powerful motor, because it's not magnetism that's making it go the second half. How many follow that explanation? Good. So what creates the movement again? What makes a motor move? Magnetism. When I ask you to describe this, your description should go something like this. When you attach the electricity, the battery, to the coil produces magnetism. You get a north and south pole. The north and south will be attracted. The north and north will repel, causing the coil to turn. 1/2 turn. If opposites attract, why doesn't it just go halfway and stop? Well, why doesn't it just stop here? Because it's turned off. You have to figure out what it is about the design of our coil that allows it to turn it off at this point. It turns off. What keeps it going then if we turn it off? Momentum. That's the energy of the spin that we already gave it. Okay? So it has enough momentum to get back up to the top, and then we turn it on again. Third question there says, what effect does the distance from the magnet have on the spinning motor? What would it do? If we move the magnet farther away, what would it do? Would it spin faster, slower, or make no difference? Why would it spin slower? Because the magnetic field is weaker the farther away you get from the magnet. Okay? So here's my permanent magnet, here's my coil. If I get farther away, I have less to be attracted to and less to repel me, less to push off of. You get far enough away, would you not do that? That's why I ask you to put them on the leg of your desk. Because I know you're going to play with them, they're going to fall on the ground, they're going to break, and then you won't be able to do it. Please put the magnets on the leg of your desk right now. They're on your desk, put them there. Out of sight, out of mind, that way they won't get knocked off by us. Thank you. So, like I said to you guys before, it's like trying to run when you're falling through the air. I can push you off a building, little feet can go back and forth, but if you have no ground to push off of, you're not going to go anywhere. If I have no magnetism here to be attracted to or repelled by, I'm not going to go anywhere. So I want to get those two things very close. In a real motor, they are very close, almost touching, because we get more magnetism there, more to push off of. What if I were to replace this D-cell battery with like a car battery? Spin faster, slower, or no effect? Faster, definitely. Bigger battery is going to have more flow, more current. More current's going to give me more magnetism. More magnetism is going to cause it to be even more attracted, even more repelled, and spin even faster. There's a question on the homework that asks, how can we get the motor to spin the other way? Well, Nathan already mentioned one. How can we get it to spin the other way? There's two ways. Switch the wires. Good. If we switch the wires, what are we really doing? Switching the poles on the, what's this thing called? Coil, or electromagnet is the other name. What's the other way? Besides switching the wires, the connections, what else can we do? Flip the no, not the battery. That would be the same as switching the wires, switching the connections.
Flip the permanent magnet?
Yeah, if we flip the permanent magnet over, then we change the direction those lines of force are pointing and encourage it to go the other way. Okay? So those are the answers to the two questions about how can we change the direction the motor spins. If you get yours to work, hopefully you get a chance to even try that out. Okay? Any questions? You should have all the answers to our questions on the homework. Don't forget that tomorrow you also have what? A quiz. Okay? All right. I'm going to walk you through this step by step. You're welcome to work ahead, although people tend not to do too well when they work ahead. First step was to straighten out the wire, which all of you should have done. You got a clear space to work on in the middle of your desk. You put the other stuff out to the side. Got a nice smooth wire. Start by measuring out 7 centimeters. 7 centimeters of the wire. Not inches, centimeters. That's pinky widths. Grab onto that 7 centimeters and hold that 7 centimeters in your hand. The wire was 60 centimeters long, so how much is sticking out the end? 53. So the long part is sticking out the end. You're holding on to the 7. Grab that AA battery, hold the wire down on the battery, and wrap it around tightly around the AA battery. Squeeze your turns together and make sure it's tight around the battery. Keep wrapping until you have how much left on the other end? 7 centimeters, just like when we did our other coil. Okay? Keep wrapping until I have 7 centimeters on the other end. What?
I don't have a double A battery.
Get it out of your tray at the end of your row. That's why I wrote the list of things on the board. So you have a little checklist. Okay, once you get to the other end and you got 7 centimeters straight on the other end, just hold it on the battery tightly, like I am there. What you want to be able to do, we're just using the battery as a form, as a shape to wrap it around. I want to be able to pull the battery out. If I'm squeezing too tightly, I'm just going to mush my coil and flatten it out. I don't want that to happen. I don't want to hold it too loosely either because I don't want it to come unwound. So you hold it the right amount and you pull out the battery. Then you can pinch the coil together like so. Now, I'm pitching it like this. I'm going to pull one wire to the left and one wire to the right, like this. Okay? My goal is here is I'm going to be wrapping the wire. Oops, wrong direction. I'm going to wrap the wire around through the center of the coil, creating wrap points here and here. Okay? Notice that those two wrapping points are directly across from each other. It divides the coil right in half. So I'm going to take one end first, put it through the middle like so, and wrap it around twice, nice and tightly, through the center of the coil. There's one. There's two. I'm trying to keep the coil together and keep it nice and round. Then I got to make sure I go directly across from that point, straight across on the opposite side where I'm going to wrap it with the other end. Wrap it around 2 times. If you did this right, each end of the wire should be like 4 centimeters or more. One end may be longer than the other. I have one that's 4 and one that's about 5. So you got your coil look something like that. That's fine. If you're following along in the directions, we're now on to step 6 on the back. Step 6 is the part that's most often done incorrectly. So before we even touch this, let me explain what we're trying to do here. Question 6, or step 6, explains one of the questions on the homework, actually number 5. It shows how we're able to accomplish one of the things we have to do to make this motor keep going. What we want to do is remove the covering, that enamel paint, from the wire on both ends. But we don't want to remove it completely from one end. What we're doing is, imagine now that this is the coil of wire. Okay? And this is one wire sticking out of one end, and this is the other wire sticking out of the other end. Do you see how that's going to be like this? Okay. So this just kind of blows it up so you can see it better. On one end, this wire here, we're going to be removing the coating from all the way around, 360 degrees. On the other one, we're going to remove the coating. Well, actually, it should look more like this. We're going to remove that covering from just the bottom portion, just this portion, okay? So if you look at that wire, you can see the top still has the covering, the bottom of the wire has it stripped off, okay? When I used to say remove it from half of the wire, people would strip off just the end of the wire. No, that's not what I mean. I mean along the length of the wire, the entire length of the wire, you're going to remove half. So if this is your coil, when I say half, remove half, I mean remove the bottom half. That would be this edge here, the bottom half. Let's do the side where we're going to take it all off, this side over here first. If you open the scissors up and you're right-handed like me, you got the pointy ends going away from your palm. You're going to use this area right in here by the hinge, okay? You're not using this flat surface. You're not using this flat surface. You're using the corner right there. You're using the corner to scrape. So you put the wire right down there on the corner and your thumb on top. If you flatten this out like this, it isn't going to work. It's got to be turned like this. So you're putting that corner on there and drag it away from the coil towards the end of the wire. If you don't feel and hear a scrapiness, don't push harder. Adjust your angle a little bit. You should hear it scrape as you drag it away from the coil. On this end, we're getting rid of all of the red. So I'm going to keep turning it as I scrape. You press too hard, you put a nick in the wire, and then it just breaks off. So keep turning and scraping. It only takes about, I don't know, 15, 20 times, and you've got most of it off, if you're doing it at the right angle. And I'm almost there. Just a few more. So inspect the wire that you got the red off from all the way around on the one side. Okay, some of you are doing things like holding the wire and doing this. That's not what I showed. And that's not going to work for you. You're going to be here all day. What I showed is scissors first, wire on top, thumb on top of the wire. Holding it at the right angle, so you're getting it right on that corner and scraping out. Your thumb stays on top. All you do is move your whole hand away from the coil and scrape each time. So I've done the one side where I've removed everything. That would be like this side over here. Now we need to do the opposite side where we just remove it from 180 degrees. Just either the top or just the bottom. You leave the red on the other 180 degrees. So when you do the other side, you don't rotate it as much, so you just do half the wire. Hopefully you should have some ideas as to why we're doing that. Yeah,
Are we allowed to go ahead?
you can. I'm going to move ahead here in just a second. How many are up to this part? Oh, excellent. Hey, I didn't know you guys were all caught up. We're still working. All right, so at this point then, the next step says, I'm on step 7, we want to take this and wrap it around 1 or 2 more times. The idea is, guys, we probably didn't get it stripped off all the way next to the coil, so by wrapping it 1 or 2 more times, we take care of that problem.
So which one go half one?
Both of them. Okay? And when you do the wrapping, again, make sure that those 2 wrapping points are directly across from each other. Also make sure that now that you've worked with this, that the coil is still round. Nice and even and round. And the wires that come out are nice and straight. One of the things that can happen at this point when you wrap it around, the end that's shiny all the way around, not a problem. That one's rarely a problem for you. But the other one, check it. Make sure. I can see some red there. I want to make sure that either the bottom or the top is the shiny edge. Okay, either the bottom or the top. If the shiny edge faces the side, that would be facing the camera right now, that's not what we want. I'm not seeing the shiny edge facing the camera. I'm seeing it on the bottom. That's where it should be. Okay? So once you've got this shaped into a nice coil, the wire's straight, then take your ruler and check each wire. We want them to be 2 centimeters long. If they're longer than 2 centimeters, clip them off. So they're 2 centimeters. Again, if your coil is not nice and round and even like this, with the wire dividing it perfectly in half and straight out to the side, you want to straighten it out. This is an important step. So you look at it this way, is it straight? You know, this way, is it straight? Every direction. Does it look like it's straight? When you're satisfied that it is, put it off to the side. We're done with that for right now. And get your 2 paper clips. We're now up to step 8. Okay, at this point then, take one of the paper clips. You'll notice that there are 2 loops that form a paper clip. We've got the big loop around the outside, and the little loop in the middle. Get a hold of the little loop in the middle and bend it away. Pull it away from the big loop until you form a little L. Pull the little loop out of the middle, bend it away from the big loop, and form an L, like so. These are going to be our little brackets, our brushes, if you will, that are going to allow us to make the connection and keep the wires from getting all tangled and twisted as the coil wants to spin. Next, you take a single wire, a single paper clip like this, and we're going to form a hole right up here at the top by closing that little loop. So I'm hanging on to the big loop in my hand, and the little loop I'm going to close down until I make this hole right in there, like so. Okay? Notice I stop when I'm at like 90 degrees here, right angle. So there's one. Looks like that. Same thing on the other one. Make sure you do that on the little loop side. The big loop you're hanging on to, the little loop side is the one you're going to close by pulling it towards itself. Stop when you get a 90-degree angle. Take your masking tape, divide it into 4 even sections. They're going to be a couple inches each. We're referring now to the picture you see at the bottom, the very last one. You can see what it's going to look like when we're all done here. What we're going to be doing is taking these 2 paper clips and forming a little stand here in the middle. Notice that the ends, the big loop end, is the part that goes on the table, and notice that they're pointing away from each other. So there's nothing in between the 2. So you're going to set these up in the middle of your desk. Put one down first, like so, with 2 pieces of masking tape, so that this end is closest to the edge, the side of your desk. And then use your ruler to make sure that you separate the 2 paper clips by 8 centimeters. Before I put this other, I'm sorry, I said 8, I meant 4, by 4 centimeters. Before you put the other paper clip down, take your coil, check it again, make sure it's nice and straight and even, round, balanced, smooth. Slide one end in the hole. Then you can take the other paper clip and slide it on like so. We want to make sure that those 2 are 4, not 8, I misspoke, 4 centimeters apart. We also want to make sure that these 2 holes are directly across from each other in a straight line. So you move it until you see that they're lined up. We don't want the paper clip to be twisted out like this. We want it to be in a straight line across there. 4 centimeters apart, straight line so the holes line up. When you're satisfied you got in the right position, then you can tape it in place. Before you ever bring in anything else, the magnet or the battery, this is an important step, a test to make sure that the thing is balanced. I'm going to just give it a little flick, and I can see that it spins fairly freely. It doesn't wobble too much. It doesn't turn just a few turns and then stop. I've got a nice even base here. The 2 holes are directly across from each other and it seems to spin pretty well. If it doesn't, this is the time you should be reshaping your coil or moving the paper clips until they're lined up properly. At this point then, we're almost done. We take the magnets and we put them directly underneath the coil. You take your battery, make sure the 2 connections on the battery don't touch by accident. And I'm going to put one on one paper clip. You notice that I'll connect these down here at the bottom. That's less likely to move our paper clips if you do it down where you taped it. And I put the other one on there and give it a little touch and it starts to spin. If it doesn't, try spinning it the other way. Give it a little push the other way. If it wobbles back and forth, what you want to look for are things like, did you divide the coil perfectly in half? Is it nice and even and round? Did you strip the wire properly? Okay? All of those things can affect your results. Look at number 12 if you find that you can't get it to work, and read the suggestions there, and all of those might help you in getting it to work. If you get your coil to work, great. You can disconnect it from the battery and help others to get theirs working. You might also try flipping the battery and the magnet over. Excuse me, I'm still talking. You might try flipping the magnet over and see how it spins the other way. Or you might try changing your connections on the battery and see how it spins the opposite way, just like we talked about for the homework. So you're one of the diehards that stays till the very end. Well, here's the benefit. I'm going to read the questions to you right off of the electricity quiz for tomorrow. Question number 1. Electricity is the flow of blank through a blank. If you don't know the answer to that one, you've been asleep the whole time. Number 2. The atomic particles and charges are, and the answer we're looking for here is protons, neutrons, and electrons. Protons are positive, neutrons are neutral, and electrons are negative. Number 3, blank can become magnetic because it has blank electrons. The answer we're looking for is iron, nickel, or cobalt can become magnetic because they have unpaired electrons. Number 4, the particles that move easily are blank. When they build up on an object, this is called blank. The particles that can be moved easily are called electrons. The buildup of electrons on an object is called static electricity. Static means not moving, and they're building up, they're not moving yet. Number 5, groups of magnetic atoms may align to form blank. When atoms have their magnetic fields aligned facing the same way, this is referred to as magnetic domains. Number 6, which of these statements are false? A, electricity can make magnetism. B, protons are tiny magnets. Or C, magnetism can produce electricity. Of course, B is the incorrect one. Protons are not tiny magnets, electrons are. Number 7, lightning strikes when a blank from the ground joins with a blank from a cloud. Together, they form channels considered blank. Lightning forms when ionized air in the form of streamers and step leaders connect together to form a channel that works like a wire of air. The channel of ionized air that leads from the cloud to the ground is called a step leader. From the ground to the cloud is called a streamer. Number 8, a battery produces electricity through a blank reaction between two blank and one blank. A battery does a chemical reaction between two electrodes and one electrolyte. Number 9, a generator creates electricity when blank energy is used with a wire to move through blank. The energy that's moving a wire is referred to as mechanical energy, such as the energy of a machine, or when your body moves, that's a machine. So mechanical energy moves the wire through the magnetic lines of force, the invisible field of attraction that surrounds a magnet. Number 10, water flowing through a fire hose would be a good model for which of the following? High A, low V, high V, low A, high V, low A, or high A, and low V or low A. Well, a fire hose is going to deliver a great deal of water with a great deal of pressure. The more water that passes by every second, the greater the current. That would be A, so the A would be high. The fire hose would also deliver the water with a great deal of pressure or force. That would be referred to as voltage, so it would be a high V, high voltage. So the answer is high A and high V. Number 11, resistance is measured in blank and is represented by the blank. It will blank the current. Resistance is measured in units called ohms. It is represented by the omega symbol, which is the little horseshoe shape. It will blank the current. Resistance will always slow down the current, slow down the flow, just like adding boulders in a creek would slow the flow and would reduce the speed that water can go by. Number 12, copper is a good blank, which blank the flow of electrons. Copper is a good conductor. The opposite of a conductor is an insulator. Copper is a conductor. Conductors allow the flow of electrons easily. Number 13, blank or magnetite is a natural magnetic rock found near the Greek town of blank. Lodestone is the other name for magnetite, and this was first found near the Greek town of Magnesia, which is how it got its name, magnetite. Number 14,
blank discovered that electricity can make magnetism, while blank discovered the opposite. Electricity can make magnetism was discovered by Hans Oersted with his famous experiment with the battery and the compass. He was the teacher. The Englishman by the name of Michael Faraday discovered that the opposite is true, that magnetism can create electricity by breaking the lines of force. Number 15, AC stands for blank current and is produced by a blank. AC stands for alternating current and is produced by a generator. Number 16, one turn, one rotation of a generator coil is called a blank. The number of these that happen each second are called blank. One turn of a generator handle will give a cycle, a positive and negative flow of current. The number of these that happen each second is referred to as a hertz. 1 hertz would be 1 cycle in each second. Number 17, DC stands for blank current and is produced by a blank. DC stands for direct current, current that flows in only one direction, and is produced by a dry cell, wet cell, battery of any kind. Number 18, motors function like a blank, pushing and pulling towards or away from a blank. Motors function like an electromagnet. When the electromagnet is activated, it is either pulled or pushed to or away from a permanent magnet. Good luck. Good luck.